Today we're going to learn about conic sections. So there are four conic sections, meaning four geometric structures you can get by intersecting a plane and a set of tip-to-tip cones. I'll show you what I mean. So here are the four conic sections. So if you have two, these are right-angled cones that are identical and they touch at the tip and they share a center line. So this line right here would be the center line. If you take a plane that is orthogonal, which means perpendicular in all directions, to that center line, you get an intersection that's a circle. So if that plane is perpendicular to the center line, then the outline is a circle. Oops, I got fat elbow. If you tilt the plane a little bit, then you get what is called an ellipse, which is like an oval, only an ellipse is a very structurally defined oval. Oval just means egg-shaped. It comes from the root word ova, which means egg. So anything that's egg-shaped is oval. And an ellipse is stronger than an oval. An ellipse has two different axes of symmetry. So if I had an egg, so that only has one axis of symmetry, but an ellipse has two. It has a major axis, the long one, and a minor axis. And an ellipse is very similar to a circle. In fact, their equations are identical in every way except one. There's one very small difference between the equation of a circle and the equation of an ellipse. And just because it has two axes of symmetry doesn't mean that it is an ellipse. So if I had something like this, it is not an ellipse. Because it has straight sides. An ellipse doesn't actually have straight sides. All right, so if we go back to our page of conic sections, if you take that ellipse plane and you fold it more so that it intersects both cones, then you get what's called a hyperbola. And notice the dotted line on the left has a hyperbola where the line is not straight up and down, and the one on the right is straight up and down. And in both cases, you create something that looks like this. So it kind of has two parts. Now, it's certainly not a function. It doesn't pass the vertical line test, but neither is a circle or an ellipse. And you could also, depending on the equation, you can have a vertical hyperbola or even a horizontal hyperbola. I'll show you. And then if you were to continue to move that plane and you made the plane parallel to the bottom cone, then the hyperbola turns into a parabola, which is different. So you know what a parabola is. It's a quadratic equation graph. But there's a big difference between a hyperbola and a parabola. A parabola has sides that always get steeper. So if we were to mark the steepness of this parabola, this set of lines that I'm drawing approaches straight up and down. As I move to the right, eventually it's going to be really close to straight up and down. But a hyperbola is not that way. A hyperbola approaches a set of asymptotes. So there's an X, sort of, and it looks like this. So a parabola, the steepness approaches infinity, meaning that line approaches straight up and down. But in a hyperbola, the line approaches some other line that's not straight up and down. And then the same thing happens on the other side. So structurally, they're kind of similar, but the end behavior is quite different. And a hyperbola has two sides, and a parabola only has one. Well, all conic sections are based on the graph of x squared. All of them. Now, you can get really technical. Go back to that page. And you could say, oh, well, if I draw a line right through a plane right through the middle, then the intersection is a single point. So you could claim that a point is a conic section, but we don't. And then if you ran a plane down one of these sides, the intersection would be a straight line. If you were to move it off that straight line, it would be a parabola. But if it hits that, then it would be a line. So technically a line is, and there is a way to make two lines, but we're not going to worry about it. So a parabola is the graph y, oh boy, y equals x squared. The graph of a circle is x squared plus y squared equals some value, a constant. So this is a parabola and a circle. An ellipse is x squared plus y squared, where you divide x by some number and you divide y by, some other number. So this is the major and the minor axis. Whichever one of these numbers is bigger, if the x is bigger, then it's a horizontal ellipse. If the y is better, then it's a vertical ellipse. Well, what if a and b were the same number? It would be a circle, right? So the only difference between these is these are both over 1, and these are divided by two different numbers, and that stretches it one way or the other. And then a hyperbola is either x squared minus y squared or y squared minus x squared. One of those is vertical and one of those is horizontal. So all conic sections have equations that are really close to each other. They're all some version of x squared. Okay? And you'll notice this one is the only function. All of the others fail the vertical line test because all of them have a y squared. And anytime you have a y squared, you run the risk of failing the vertical line test. The parabola, just a single parabola. That's the only one that's function. But you could flip these around and you could do x equals y squared, and that would be this kind of parabola, and that's not a function. Because, again, we have y squared. Okay? So today we're going to play, we're going to kind of figure out how circles and ellipses relate to one another. So we have a worksheet. It's not this one, though. I updated it. It tells you what you need. So everybody needs to get their own paper, and the instructions say, for this task you will need a piece of cardboard, you might want two, 4 sheets of regular paper, it's over on the table, 3 pieces of string of different lengths, no longer than 10 inches and no shorter than 6. So you can make like a 6 and 8 or a 10 or a 6, 7, 8 or 7, 8, 9, whatever you want. But the shortest one has to be at least 6, and the longest one can't be bigger than 10. So you're going to take those strings, and you're going to tie a knot so that the strings make a ring. No, as long as it fits in there, it's fine. But I would get a ruler to measure it. Because if you make them too small, then it won't really work. And if you make it too big, you'll go off the paper. Okay? So you're going to tie each one, so you'll have 3 different pieces of string tied in a circle. Okay? Then you're going to take the push pins, and you're going to stick it in the cardboard, and I recommend that you get 2 pieces of cardboard. And when you push it in, don't push the pin till it's flat. Push it in so there's just enough room for the string to sit underneath that. Okay? So for the first one, you're going to put a pin in there. Then you're going to take your ring, and you're going to stick it right there. And then you put your pencil inside the ring, and you pull it tight. So it kind of looks like this. And then you're just going to trace around, and it's going to make a circle. That makes sense? So you use that ring to pull as tight as you can, and you trace out a circle. Okay, and you're going to do that with all the others. And then later on, you're going to take 2 pins, and then you're going to put your ring around the pin, and then you're going to pull that tight, so it looks something like this. And then keeping that ring tight, you're going to trace around again. Does that make sense? Maybe, so maybe I can show you. So you'll have two pins like this, and you'll take your pencil and you'll trace it around like that. Okay? And on number 3, it says you're going to go all the way around. Yeah. Number 3 says replace the paper and place 2 pins far enough apart that the shortest string still fits around the pins. So if I were to say this is my shortest string, that would be too tight because there's really not room to get my pencil around the pin. So you got to pull it in a little bit so there's enough room to pull your pencil around. Okay? And then later on you're going to move it out too big for the small string, and then use this for the other string. 1 and 2 go on the same paper, 3 and 4 go on the same paper, number 5 gets its own paper, and number 6 gets its own paper. Okay? You're allowed to work with one partner, so you and a partner, each of you fill out your own paper, but you only need one set of materials. And then just take turns drawing the shapes. All right? Once everybody's done with that, we'll talk about a couple things. Go to work. Okay, now that you've drawn your shapes, most of them, let's talk a little bit about an ellipse. So we have ellipses all over the universe. Not too many on Earth, but the orbit of planets are elliptical. Okay? Now, each one of those pins in the things that you created are called, well, they're each a focus, and the plural form of focus is foci. So if you were to look at the orbit of Earth around the sun, so here's the sun, and the orbits are not perfectly circular. Well, that doesn't look circular. There we go. They're a little bit elliptical. Now that's exaggerated, but you'll notice that the sun rests at one of the two foci. So actually on Earth, we are closer to the sun in the northern hemisphere in the winter than we are in the summer. I mean, it's not significantly closer, but it is closer. You know, maybe, I don't know, 500,000 miles or something. You'd have to look it up. And the orbit of Pluto is so elliptical that the orbit of the next closest planet, actually, well, okay, it was when I was in school. So sometimes Pluto is closer than, what is it, Neptune? Uranus? Neptune? I don't remember. But there have been times where Pluto has been closer than the next closest planet, the sun. Is it Neptune? And the orbit of Pluto is highly, well, as far as planets go, it's highly elliptical. Now, comets, so I don't know if you guys know, but over Thanksgiving break, there was that comet that flew around the sun, and it didn't make it. It got too close. Burned up. Yeah. So if you were to look at, so here's the sun, and we have the inner planets, then we have the outer planets. Each one of those is an elliptical orbit. Comets do the same thing, but with comets, this is what the orbits look like. Yeah. So, and there are two foci there, and the sun rests at one of the two foci. And what happens, let's say that you keep the strings the same length, what happens as you move those pins closer and closer together? It's more circular. Well, what happens when the two pins are in the same place? Then it becomes a circle. And then what happens as you move the pins further apart? It gets narrower. What if I kept the pins in the same place, and I used a really small string and a really big string, how would they be different? Other than the size, of course. The little one is going to be very elliptical, and the big one would appear circular. Now, if you made your string larger and larger and larger, the shape is going to approach a circle, but it will never actually be a circle because the foci are in two different places. Okay? Now, there are also foci, well, a focus in a parabola and a hyperbola actually has two foci. So you can actually use string to create parabolas, hyperbolas, circles, and ellipses. You just kind of have to change how you use the string. One more interesting thing about ellipses. If you take any focus and you draw a line to the edge of the ellipse, and then you draw a line from that point to the other focus, that distance is constant. The distance from one focus to the edge to the other focus is always the same. So if I were to do over here like this, that distance would be constant, and I can prove it to you. Okay? Because this string is always the same size, right? Well, this distance is constant. So if I subtract off the distance between the two foci, what's left? Two pieces that are always, I mean, the two pieces change, but their sum is always the same length. So this red distance has to be the same as the blue distance, which has to be the same as the green distance, because it's the same piece of string, and all we're doing is subtracting off that one distance. So that is one definition of the focus definition of an ellipse. An ellipse is the set of all points that's a constant distance between two foci. So if I were to measure this length and measure that length and measure that length, it's always going to be the same, no matter where I move that point. So as you trace your pencil around the ellipse, that is the set of all points that's constructed using the sum of the distances of the two foci. Anyways, it gets a little complicated. But that's where an ellipse comes from. So we're done for today. Each of you staple 2 of your drawings to your worksheet and hand it in. And then, so you had four papers. 2 of each needs to be stapled to your thing. And then, can you guys pick up all the string and papers on the ground and put the desk back in order, please?